Welcome to the first video in the LPIC-1 Exam 101 video series. To earn LPIC-1 certification, the person who is getting the certification must pass Exam 1 and Exam 2, kind of like how the CCNA used to be in two parts. So this series is going to be all about Exam 1. I will be able to schedule and attempt the LPIC-1 exam that allows you to, oh, wait, never mind. At the end of this series, I will be able to schedule the first exam for the LPIC-1, but I will not be able to get the LPIC-1 certification in full until I completed another series studying for exam number 2. Okay, so I'm going to share my screen here and we're just going to get started right away. So I've got my channel here, previous video loading. Then I've got, here we go. This is the first topic in the LPIC-1 exam. The first topic is system architecture. The first subtopic is determining and configuring hardware settings. All right. So key knowledge areas, enable and disable integrated peripherals, differentiate between the various types of mass storage devices, determine hardware resources for devices, tools and utilities to list various hardware information, for example, LS USB, LS PCI, further LS related commands, tools and utilities to manipulate USB devices, conceptual understanding of sysfs, UDEV, and dbus. So here's a partial list of the files, terms, and utilities that we'll be using. We'll be using /sys/proc/deb. We'll be using modprobe, lsmod, lspci, and lsusb. All right, so let's move on to the next lesson. So we're going to proceed to lesson 1. All right, lesson 1 is determining and configuring hardware settings. Introduction. Since the early years of electronic computing, business and professional computer manufacturers have integrated a variety of hardware parts in their machines, which in turn need to be supported by the operating system. That could be overwhelming from the operating system developer's perspective, unless standards for instruction sets and device communication are established by the industry. Similar to the standardized abstraction layer provided by the operating system to an application, these standards make it easier to write and maintain an operating system that is not tied to a specific hardware model. However, the complexity of the integrated underlying hardware sometimes requires adjustments in how resources should be exposed to the operating system so it can be installed and function correctly. Some of these adjustments can be made even without an installed operating system. Most machines offer a configuration utility that can be executed as the machine is turned on. Until the mid-2000s, the configuration utility was implemented in the BIOS, Basic Input Output System, the standard for firmware containing the basic configuration routines found in x86 motherboards. From the end of the first decade of the 2000s, machines based on the x86 architecture started to replace the BIOS with a new implementation called UEFI, Unified Extensible Firmware Interface, which has more sophisticated features for identification, testing, configuration, and firmware upgrades. Despite the change, it is not uncommon to still call the configuration utility BIOS, as both implementations fulfill the same basic purpose. Note, further details on the similarities and differences between BIOS and UEFI will be covered in a later lesson. Device activation. The system configuration utility is presented after pressing a specific key when the computer is turned on. Which key to press varies from manufacturer to manufacturer, but usually it is DEL. So the delete key, yeah, so I'll show where it is on my keyboard. On my keyboard, the DEL, there's no key that says DEL specifically, but there's a key here that says delete. That's the key that's being referred to. Notably, not backspace, not escape, delete. Or one of the function keys such as F2 or F12. The key combination to use is often displayed in the power on screen. In the BIOS setup utility, it is possible to enable and disable integrated peripherals, activate basic error protection, and change hardware settings like IRQ, interrupt request, and DMA, direct memory access. Changing these settings is rarely needed on modern machines, but it may be necessary to make adjustments to address specific issues. There are RAM technologies, for example, that are compatible with faster data transfer rates than the default values. So it is recommended to change it to the values specified by the manufacturer. Some CPUs offer features that may not be required for the particular installation and can be deactivated. Disabled features will reduce power consumption and can increase system protection, such as CPU features containing known bugs can also be disabled. If the machine is equipped with many storage devices, it is important to define which one has the correct bootloader and should be the first entry in the device boot order. The operating system may not load if the correct device comes first, if the incorrect device comes first in the BIOS boot configuration list. Device inspection in Linux. Once devices are correctly identified, it is up to the operating system to associate the corresponding software components required by them. When a hardware feature is not working as expected, it is important to identify where exactly the problem is happening. When a piece of hardware is not detected by the operating system, it is most likely that the part or the port to which it is connected is defective. When the hardware part is correctly detected but still does not properly work, there may be a problem on the operating system side. Therefore, one of the first steps when dealing with hardware-related issues is to check if the operating system is properly detecting the device. There are two basic ways to identify hardware resources on a Linux system: to use specialized commands or to read specific files inside special file systems. Commands for inspection. The two essential commands to identify connected devices on a Linux system are LSPCI, shows all devices currently connected to the PCI peripheral component interconnect bus. PCI devices can be either a component attached to the motherboard, like a disk controller, or an expansion card fitted into a PCI slot, like an external graphics card. LSUSB lists USB Universal Serial Bus devices currently connected to the machine. Although USB devices for almost any imaginable purpose exist, the USB interface is largely used to connect input devices, keyboards, pointing devices, and removable storage media. The output of the commands LSPCI and LSUSB consists of a list of all PCI and USB devices identified by the operating system. However, the device may not be fully operational yet because every hardware part requires a software component to control the corresponding device. This software component is called a kernel module, and it could be part of the official Linux kernel or added separately from other sources. Okay, before I continue, I'm going to take a quick break here and look at my own PC. Hands-on practice is really important for these kinds of certs. So I'm going to type in LSPCI, and it looks like we've got a problem here. Cannot find any working access memory. I'm going to try sudo LSPCI. Okay, still same problem. So now I'll try LSUSB. Same problem. We'll try sudo LSUSB. Same problem. Okay, so it looks like there's going to be some sort of issue with running these commands on my Windows machine. I do have the subsystem for Linux enabled, so you can see I do have a bash prompt, and I do have some sort of virtualized Linux features and components enabled on my Windows machine. But the best way, in my opinion, to follow along with this and get hands-on exercise would be on an actual Linux machine. I do have an actual Linux machine. It's my R610 Blade server. Right now it's powered down, but I will power it up. I'll power it up right now. So I'll pause the video. I'll come back in like 30 seconds. Power it up, and then come back and read this part. So I'll be back in just a minute. All right, I'm back. I've got a hands-on device powering up now that I can do all of these commands on remotely through SSH. I've got my internal router here. If I click on attached devices, I should see that home lab listed here once it's booted up, and then I can SSH to the IP address. But in the meantime, let's keep reading the learning materials. Linux kernel modules related to hardware devices, also called drivers, as in other operating systems. Linux kernel modules related to hardware devices are also called drivers, as in other operating systems, such as Windows. Drivers for Linux, however, are not always supplied by the device's manufacturer. Whilst some manufacturers provide their own binary drivers to be installed separately, many drivers are written by independent developers. Historically, parts that work on Windows, for example, may not have a counterpart kernel module for Linux. Nowadays, Linux-based operating systems have strong hardware support, and most devices work effortlessly. Commands directly related to hardware often require root privileges to execute or will only show limited information when executed by a normal user. So it may be necessary to log in as root or execute the command with sudo. The following output of command lspci, for example, shows a few identified devices. And then we saw, and I tried to do that on my Windows computer, there was an issue with that. Can't find any working access member. Do it with sudo. Same issue. So obviously there's some sort of problem. Hopefully once my Dell R610 server comes up, that will not be a problem anymore. Looks like it's still booting up. It might take some time for it to come up. Oh, no, it's up now. Okay, good. All right, so I'm going to take a moment here and try to get on that server. Connection refused, so I think the SSH daemon is probably not loaded yet. Yeah, so it's still going to need a little bit of time to come up. In the meantime, I'll keep reading. The following output of command LSPCI, for example, shows a few identified devices. So we've got graphics card, we've got the network controller, looks like a for wireless networking. Yep, looks like a wireless network controller. Then we've got a sound card here. We've got I'm not sure what this is. A FireWire. Let's take a look at what this is because I'm not familiar with this. Okay, so here's what it is. Looks like it's a hmm, some sort of networking device, maybe for like wired networking. That had a wireless networking card, but this looks like it's perhaps some kind of wired networking card. Yeah, I think that's what we got here. Yep, that's what we got here. Okay, so we got graphics card, we've got a wireless networking controller, we've got a sound card, and we've got a wired networking controller. The output of such commands can be tens of lines long. So the previous and next examples contain only the sections of interest. The hexadecimal numbers at the beginning of each line are the unique addresses of the corresponding PCI device. The command LSPCI shows more details about a specific device if its address is given with the option -S accompanied by the option -B. The output now shows many more details of the device on address 04 colon 02.0. So by address, they mean the location on the motherboard where of the location of the PCI slot on the motherboard. It has a particular address that's different than, for example, an IP address, which is used to identify devices on the network. In this case, this is the address of a slot on a motherboard, in this case, a PCI slot. It is the network controller whose internal name is that. Subsystem is associated with the device's brand and model and can be helpful for diagnostic purposes. The kernel module can be identified in the line kernel driver in use, which we can see here. So this is the software kernel module that is used to uh, run this hardware component, which shows the module RT61PCI. From all the information gathered, it is correct to assume that the device was identified, a matching kernel module was loaded, the device should be ready for use. Another way to verify which kernel module is in use for the specified device is provided by the option -K, available in more recent versions of LSPCI. And we can see an example of that here. We've got the command, we've got the dash S, which allows us to give it a address. I'm not sure what I'm not sure why it's like an S. I'm not sure like what S stands for, but anyways, following the dash S option that we entered, we can provide the address of the PCI slot on the motherboard, which is 01:00.0, and then we can feed it the dot K, so we get information specifically about the kernel modules. So we can see for this video card, uh, we've got information about a kernel driver. It says NVIDIA, and then we've got information about kernel modules. So I'm not sure why both of those are listed. I would guess that it's because this device is compatible with Windows and Linux. So if it were in a Linux system, it would use this kernel driver. But if it's in a, but you know, guessing it can be problematic because it can lead to learning things that are incorrect that you'll have to unlearn later. So let's not guess, let's just move on and read the rest of the training. For the chosen device, an NVIDIA GPU board LSPCI tells that the module in use is named NVIDIA. At line kernel driver in use NVIDIA, and all corresponding kernel modules are listed in the line kernel modules Nouveau NVIDIA DRM NVIDIA. The command ls USB is similar to ls PCI, but lists USB information exclusively. ls USB, so there we go. The USB information is now listed exclusively. So we don't see other information like the kernel modules. We only see the, or wait, oh no. So this is another slot on the motherboard. We had PCI slots, but now we're looking at USB slots, and we're not seeing any information about PCI slots anymore. So you can see we've got quite a few more, quite a larger number of things in the USB slots plugged into the USB slots. They're not plugged into the PCI slots. And the PCI slots, we only had 4 devices, which makes sense because if you think about what kinds of devices plug into a PCI slot, a keyboard, a mouse, your monitor, do those plug into PCI slots? No. And shoot. Well, let's do it this way. Let's do it this way. So, computer motherboard, and we just look at an image of the computer motherboard. Perfect. So that's because these are PCI slots here. So when you plug in your keyboard, your monitor, it does. You're dealing with something that looks like this, and not something that looks like it could plug into something like this. So when you're dealing with video cards, networking devices, uh, like network interface cards for wireless or for what have you, it will plug into some sort of PCI slot. So the connection of a video card, I don't think I have anything like that laying around here to further demonstrate that point. But let's just take a look at a video card. Yeah, so take a look at this. That definitely looks like it would fit into this slot that we were looking at earlier because it in fact does. It's meant for a PCI slot on your motherboard and not a USB slot. Okay, so yep, we've only got 4 devices in this example plugged into PCI slots, video card, networking devices, wired and wireless, and then an audio card. But when it comes to the USB slots, we've got a lot more things plugged in. We've got our monitor, we've got our mouse, uh, we've got looks like a Bluetooth adapter, maybe for like headphones or something like that. So, um, yeah, dealing with a different kind of connection. USB looks like this. It comes in A, B, C, different kinds. Just like the PCI slots, it's just similar with PCI slots. There's like PCI Express. There's like more legacy PCI slots. So, yep, it's just a matter of what plugs into to what kind of sockets there are on your motherboard. Primarily, there's two different kinds. There's PCI and there's USB. The command ls USB shows the available USB channels and the devices connected to them. As with LSPCI, Option-V displays more detailed output. A specific device can be selected for inspection by providing its ID to Option-D. Okay, so now, just like as we saw with the PCI devices, how they had a address that represented their location on the motherboard, same thing with the USBs. They have an address that represents their location on the motherboard. And it looks like it's in a different syntax. Um, and the other thing is, before, in order to plug in that address, you needed to use -S, but here it looks like you need to use -D. With the Option-T command, ls USB shows the current USB device mappings as a hierarchical tree. Okay, and hopefully yep, it's up now. The daemon for SSH started, so we should be able to run these commands, which is exciting, which will help a lot, I think, with the hands-on component. So LSPCI, there you go. Now we got a real Linux system here, not my imposter that I was using on my Windows machine. So we got all the information we could possibly want and more. You can see this is a loaded system. So now it gets kind of interesting for me because we see that the processor is included. And from what I understood, oh, or maybe it's not. But anyways, there's a lot more devices on here than I was expecting to see, and I'm wondering if it is in fact the case that each of these devices are plugged into a PCI slot. I could open it up and take a look. I do have video of me doing that later. I could pull that up to take a look, but let's just move on. It's not relevant. Take a look at the USB. Okay, there's a few things on there. So most important thing, we got that up and running, ready to go for next time. I am running out of time very quick. In fact, I think I'm out of time now. So let's bookmark this. Let's have this be the place where I start next time, and end this video right here, right now. So, okay, so. Uh, okay, so this looks like a good way to save my spots. Okay, so yep, I'm out of time, unfortunately. That's the end of this video. Thanks for watching and stay tuned for the next one.